Hello, I'm Essay, your AI essayist. Please note that all content, audio and video in this presentation are AI generated. As AI can sometimes produce inaccuracies, I encourage you to verify any factual information presented. With that in mind, let's begin. In the early 9th century, under the patronage of the Caliph al-Ma'mun, the city of Baghdad stood as the political and intellectual heart of a sprawling Abbasid empire. This vast domain, stretching from the Iberian Peninsula to the fringes of India, represented a consolidation of peoples, languages and traditions on a scale few civilizations had ever managed. Its arteries were caravan routes and sea lanes, its lifeblood the commerce in silks, spices and ideas. Yet with this immense scale came an equally immense challenge, the problem of governance. How does one administer such a colossal and diverse entity? How does one levy taxes with fairness and precision, survey land for agriculture and construction, or distribute inheritances according to the intricate prescriptions of Islamic law? These were questions of profound practical urgency, and their solutions demanded a tool more powerful and more universal than any the ancient world had bequeathed. The empire was, in a sense, a victim of its own success, generating a volume of administrative and economic data that threatened to overwhelm the very systems designed to manage it. The existing methods of calculation were a patchwork of traditions, often cumbersome and ill-suited to the task. Roman numerals, with their additive and subtractive principles, made complex arithmetic a tortuous affair. Greek mathematics, while possessing unparalleled geometric and philosophical elegance, often remained in the realm of the abstract, its focus on proof and form sometimes detached from the messy realities of commerce and statecraft. The bureaucrats of the caliphate required a new language of quantity, a system that was efficient, reliable, and crucially teachable. They needed a practical science of calculation that could be standardized and deployed across the empire, from the tax collectors in Egypt to the merchants of Samarkand. The crucible for this intellectual revolution was a remarkable institution at the heart of the capital, the Beit al-Hikmah, the House of Wisdom. Established and endowed by the caliphs, this academy was a beacon, drawing scholars, translators, and thinkers from across the known world. It functioned as a grand synthesis engine. Within its walls, the philosophical and mathematical treasures of antiquity were actively sought out, translated, and critically examined. Papyri from Greece carrying the works of Euclid, Archimedes and Ptolemy were rendered into Arabic. Sanskrit manuscripts arrived from India, bearing a revolutionary system of positional notation and a symbol for zero, concepts with profound computational potential. Persian astronomical tables and administrative traditions added another layer of sophisticated empirical knowledge. The atmosphere was one of intense, state-sponsored intellectual fervor, a collective enterprise to harness the entirety of human knowledge for the advancement of the civilization. Into this vibrant milieu steps the figure of Muhammad ibn Musa al-Khwarizmi. Our knowledge of his life is sparse, pieced together from prefaces to his works, and mentions by later commentators. We believe he was of Persian origin, his name suggesting a connection to the region of Khwarezm, south of the Aral Sea, in modern-day Uzbekistan. What is certain is that he became a preeminent scholar at the House of Wisdom during its golden age under al-Ma'mun. He was a man perfectly positioned at the confluence of these powerful intellectual currents. He had access to the geometric rigor of the Greeks, the algebraic and astronomical traditions of the Babylonians and Persians, and the transformative numerical innovations of the Indians. Al-Khwarizmi's genius lay in his ability to see the practical power latent within these disparate streams of thought. He was a polymath whose work spanned mathematics, astronomy and geography, each field informing the others. He absorbed the philosophical depth of Greek geometry, but his gaze was firmly fixed upon the concrete problems that preoccupied the Abbasid administration.
He saw in the elegant Indian system of numerals a key to unlocking unprecedented computational speed and clarity. He perceived that the case-by-case, rhetorical solutions to problems of inheritance or trade could be unified under a single, powerful, and abstract methodology. His project, sponsored by the Caliph himself, was fundamentally a practical one. The sophisticated demands of Islamic inheritance law, known as Fara'id, presented a particularly thorny set of challenges. These laws, derived from the Qur'an, dictate a complex and precise division of an estate among various heirs, with fractions depending on gender, lineage, and relation to the deceased. Calculating these shares using existing methods was an exercise in frustration, prone to error and endless dispute. A typical problem might involve dividing an estate where a man leaves behind 2 sons, a wife, and his own mother, with each entitled to a specific, fractional share. The calculations became even more convoluted when debts or bequests were involved. What was needed was a general procedure, a reliable mechanism that could take the particulars of any inheritance case and produce the correct shares systematically. This was the world that awaited al-Khwarizmi, an empire in need of a universal calculus, a library filled with the latent potential of global knowledge, and a patron demanding tangible results. His response would be to forge a new discipline from the raw materials at his disposal. He would create a systematic method for manipulating unknown quantities, for setting up problems as equations, and for solving them through a series of standardized, repeatable steps. He would author a text so foundational, so clear, and so powerful that its very title would give a name to this new science. His work was an answer to a civilizational call, an intellectual leap born of administrative necessity. In his hands, mathematics would become an essential instrument of state power, economic efficiency, and legal clarity. The stage was set for the creation of a procedural language that would in time reshape the world's relationship with number and logic itself. What would emerge from his pen was a compendious book on a method of calculation that would lay the groundwork for centuries of mathematical development, a system built upon the twin pillars of completion and balancing. The very title of the work that answered this civilizational call, Al-Kitāb al-Mukhtaṣar, Ḥisāb al-Jabr, wa-l-Muqābala, the Compendious Book on Calculation by Completion and Balancing, announces its revolutionary purpose. Composed around the year 820 in Baghdad's House of Wisdom, this text represents a pivotal moment in the history of human thought. In his preface, al-Khwarizmi addresses his patron, the Caliph al-Ma'mun, and outlines his ambition with remarkable clarity. He presents his work as what he calls the easiest and most useful for arithmetics, a tool intended for humankind's constant need in cases of inheritance, legacies, partition, lawsuits, and trade. He also includes its utility in the surveying of lands, the digging of canals, and other geometrical computations. His aim was profoundly practical, seeking to provide a reliable, systematic calculus for the administrators, judges, and merchants of a burgeoning empire. The problems they faced were complex. Islamic inheritance law, or Fara'id, for instance, involved meticulously prescribed fractional divisions of an estate among numerous heirs, a task that could quickly become a computational labyrinth. Existing methods were often ad hoc, relying on rhetorical descriptions and specific solutions for specific problems, lacking a universal abstract framework. Al-Khwarizmi's genius was to devise such a framework. He began by identifying the fundamental quantities in these problems, a simple number, or dirham, the unknown quantity, which he called a root or jidda, what we would today represent with the variable x, and the square of that unknown, which he called mal, meaning wealth or property, our modern x squared. From these three elements, he constructed his entire system. The power of his method resided in two elementary, yet transformative, operations: al-Jabr and al-Muqābala. Al-Jabr, which gives us our modern word algebra, can be translated as restoring or completion. Its function was to eliminate negative quantities from an equation. Since the concept of negative numbers as workable entities was undeveloped, any term involving subtraction posed a conceptual and computational barrier. Al-Jabr addressed this by adding the same quantity to both sides of an equation to make all terms positive. For example, in an equation we might write as x squared equals 40x minus 4x squared. The term minus 4x squared is problematic. Applying al-Jabr, one would add 4 squares to both sides, restoring the balance and yielding a new, more tractable equation: 5 squares equals 40 roots, or 5x squared equals 40x. The equation is healed, its terms made whole and positive. The second operation, al-Muqābala, means balancing or reduction. After al-Jabr ensured all terms were positive, al-Muqābala simplified the equation by subtracting identical quantities from both sides. Consider an equation like 50 plus a square equals 29 plus 10 roots. Through al-Muqābala, one would reduce the numbers by subtracting 29 from both sides, yielding 21 plus a square equals 10 roots. The process creates the most streamlined form of the equation, balancing the two expressions by cancelling out redundant terms. It is a principle of elegant efficiency, a mathematical razor seeking the simplest possible statement of the problem. Through the disciplined application of these two procedures, al-Khwarizmi demonstrated that any linear or quadratic equation could be reduced to one of 6 canonical forms. This act of classification was itself a profound intellectual achievement. It imposed order on a chaotic universe of individual problems, revealing an underlying structure. The 6 standard forms, all expressed rhetorically with positive coefficients, were first squares equal to roots, such as x squared equals bx, second squares equal to a number, x squared equals kers, and third roots equal to a number, bx equals kers. These 3 were the simplest cases. The true complexity lay in the final 3 types, which involved combinations of the terms: fourth, squares and roots equal to a number, x squared plus bx equals kers, fifth, squares and numbers equal to roots, x squared plus bx equals bx ids, and sixth, roots and numbers equal to squares, bx plus bx squares, x squares. This 6-fold division was a direct consequence of the mathematical world he inhabited, a world without negative coefficients or a formal concept of 0 as a standalone number. In our modern notation, these 6 cases would collapse into the single general quadratic equation x squared plus bx plus c equals zeros, where the coefficients a, b and c can be positive, negative, or 0. For al-Khwarizmi, whose system required each term to represent a tangible positive quantity, these 6 distinct forms were a logical necessity. For each of the 6, he provided a clear step-by-step recipe for finding the value of the root. His method was a pure algorithm, a finite sequence of instructions that, if followed precisely, would guarantee a solution. To give his abstract procedures the unimpeachable authority of classical mathematics, al-Khwarizmi provided geometric proofs for his solutions, particularly for the 3 complex quadratic cases. For an equation like a square and 10 roots are equal to 39 dirhams, our x squared plus 10x equals 39. He would construct a square of side length x. To this he would attach 4 rectangles, each with sides of x and 10/4, or 2.5. The total area of the central square and these four rectangles is x squared plus 10x, which the equation states is equal to 39. To complete this larger shape into a perfect square, one must add four small corner squares, each with an area of 2.5 squared, or 6.25. The total area of the four small squares is 25. Adding this to the original 39 gives a total area for the large completed square of 64. The side length of this large square must therefore be the square root of 64, which is 8. Since this side length is composed of the original x plus 2 of the small rectangle's widths, it equals x plus 5. If x plus 5 equals 8, then the root x must be 3. This visual geometric demonstration provided an intuitive and rigorous validation for his algebraic algorithm. The intellectual leap here is staggering. The object of study was the equation itself. The procedures of al-Jabr and al-Muqābala operated on the structure of the equation, manipulating it as a formal object. The specific context, be it land, money, or inheritance shares, became secondary. Al-Khwarizmi had forged a new level of abstraction, a universal problem-solving engine. He created a discipline where the goal was to find a general method, a systematic process applicable to an entire class of problems. This procedural approach, this focus on a sequence of operations to achieve a result, was the conceptual core of his contribution. The Compendious Book, while written as a practical manual, became the foundational text of a new theoretical science. Its title gave the science its name, and its method laid the groundwork for a mode of thinking that would define computation for centuries to come. The logic was in place. What this powerful new algebra awaited was a correspondingly powerful system of notation to unleash its full potential, a system that another of al-Khwarizmi's great works would champion. The abstract engine of algebra, with its powerful logic for solving the unknown, required a fuel of commensurate elegance and efficiency. A general method for finding a solution is one thing. Performing the actual calculations to arrive at a specific number is quite another. The world in which al-Khwarizmi worked, for all its intellectual vibrancy, was a world computationally constrained. The arithmetic of empires, of merchants, of astronomers, was a laborious affair, mired in the clumsy architecture of the numeral systems inherited from antiquity. Imagine a state treasurer in the Abbasid court, tasked with calculating the annual tax revenue from a dozen provinces, each with complex production figures. Or picture a merchant in the bustling souks of Baghdad, attempting to determine the profit on a caravan of silk, with costs and sale prices involving large, unwieldy numbers. The tools at their disposal were fundamentally inadequate for fluid, complex calculation. The Roman system, still in use in parts of the wider world, was an additive and subtractive jungle of symbols. Multiplying cxx30 by x11 or 123 by 47, was an esoteric task reserved for specialists, a process involving breaking down numbers into constituent parts and performing a series of separate error-prone additions. Greek numerals, which used letters of the alphabet, posed similar challenges. The primary tool for serious calculation was the dustboard or the abacus, a physical device of beads and rods. While effective in skilled hands, the abacus had a critical limitation. Its memory was ephemeral. Intermediate steps in a long calculation vanished with each new arrangement of beads, leaving the final result with little in the way of a verifiable trail. An error made midway through was devilishly difficult to trace. The process of calculation was a performance, a physical manipulation, rather than a written, repeatable record. This was the computational bottleneck of the 9th century, a world rich in problems but poor in the symbolic technology to solve them with ease and accuracy. Into this environment, al-Khwarizmi introduced a second, equally revolutionary work, a slender volume whose impact would ripple through history, shaping the very language of science and commerce. Known to us through its Latin translation Algoritmi de Numero Indorum, or al-Khwarizmi on the Hindu art of reckoning, this text was a masterclass in practical clarity. In it he turned his attention from the abstract structures of algebra to the foundational particles of mathematics, the numbers themselves. He became the great champion of a system that had been developing for centuries in India, a decimal system employing 9 elegant symbols and a 10th, transformative concept. His genius here was one of synthesis, exposition, and powerful advocacy. He laid out the Hindu numerals, the ancestors of our modern 0, 1, 2, 3, 4, 5, 6, 7, 8, and 9, and proceeded to demonstrate their profound superiority for all forms of arithmetic. The book is a user's manual for a new age of computation. It provides clear step-by-step instructions for addition and subtraction, and then, crucially, for multiplication and division, operations that were nightmarishly complex with older systems. He explained how to handle fractions and the extraction of square roots. The entire treatise is imbued with a sense of purpose to provide a complete self-contained method for anyone who needed to calculate. One can imagine the intended audience, the scribes, the merchants, the engineers and the astronomers of the House of Wisdom, who were suddenly handed a tool that replaced a laborious craft with a systematic science. The twin pillars of this new system, which al-Khwarizmi so brilliantly expounded, were the principle of place value and the symbol for 0. Place value, the idea that the magnitude of a digit depends on its position within a number, was a conceptual breakthrough of the first order. In the number 333, each 3 represents a different value, 330 and 3, a feat of informational density that older systems could only approximate with a confusing profusion of separate symbols. This positional notation was what made arithmetic an elegant paper-based activity. Columns could be aligned, carrying and borrowing could be systematized, and the entire process could be written down, checked, and preserved. The keystone of this entire arch was the 10th symbol, the dot or small circle the Arabs called sifr, meaning empty. This was the placeholder, the symbol for nothing that allows everything else to have its proper place. The difference between 37, 307, and 370 is impossible to represent cleanly and unambiguously without a character for that empty space. The Latin translation of sifr gave us the word cipher, and through a different linguistic route, the word zeros. Al-Khwarizmi's work demonstrated that this emptiness was a potent mathematical operator. It was the device that made the place value system function, the silent partner in every calculation. This introduction of 0 into the mainstream of Mediterranean and European thought was among the most significant intellectual transfers in history. It provided the missing piece that allowed for the full flowering of written algorithmic calculation. Here we arrive at the most personal and enduring part of al-Khwarizmi's legacy. When his book on the Hindu numerals was translated into Latin, his own name, in the title Algoritmi de Numero Indorum, became inextricably linked with the methods described within. The procedures he outlined, the finite step-by-step sequences of operations for adding, multiplying or finding a square root, came to be known as algorithms and eventually algorithms. The man's name became the name of the process itself. It is a rare and telling tribute when a scholar's identity becomes synonymous with a fundamental concept. An algorithm is the very essence of what al-Khwarizmi taught, a precise, unambiguous, and effective procedure for solving a problem or performing a computation. Every time we use a search engine, follow a recipe, or witness a computer execute a command, We are seeing the distant echo of the procedural thinking he codified. His work transformed arithmetic from an art of approximation on a counting board into a science of precision on paper. This popularization of the Hindu-Arabic numeral system was the necessary lubricant for the engine of algebra he had already built. It provided the practical means by which his abstract equations could be solved and applied to the real world. The Caliph's accountants could now manage the empire's finances with newfound accuracy and transparency. Engineers could perform the calculations needed for vast construction projects. And astronomers, a group to which al-Khwarizmi himself belonged, were equipped with a computational toolkit powerful enough to chart the subtle and complex movements of the heavens, a task that would form the next great chapter of his intellectual journey. This popularization of the Hindu-Arabic numeral system was the necessary lubricant for the engine of algebra he had already built. It provided the practical means by which his abstract equations could be solved and applied to the real world. The Caliph's accountants could now manage the empire's finances with newfound accuracy and transparency. Engineers could perform the calculations needed for vast construction projects, and astronomers, a group to which al-Khwarizmi himself belonged, were equipped with a computational toolkit powerful enough to chart the subtle and complex movements of the heavens, a task that would form the next great chapter of his intellectual journey. For the scholars of 9th century Baghdad, the celestial sphere was a domain of immense practical and spiritual significance. The cosmos was at once a divine clock, a sacred calendar, and a universal compass. The precise determination of prayer times, the correct orientation toward Mecca for daily worship, and the accurate prediction of the new moon to mark the beginning of Ramadan all depended on a mastery of astronomy. This was a science where tiny errors in calculation could cascade into profound ritual and social consequences. The intellectual ambition of the Abbasid court, centered in the House of Wisdom, demanded an astronomical model that was the most accurate and comprehensive in the world, one befitting the flourishing civilization it served. The challenge was to synthesize and surpass the formidable legacies of the past. The astronomers of the Caliphate inherited two main streams of celestial knowledge. From the Hellenistic world came the towering achievement of Claudius Ptolemy, whose Almagest presented a sophisticated geocentric model of the universe, a system of epicycles and difference that explained planetary motion with remarkable predictive power. Its mathematical foundation, however, rested upon the geometry of chords, a system that, while effective, was notoriously cumbersome for calculation. From the east through Persia came the astronomical traditions of India, encapsulated in texts known as Siddhantas. These works offered a different mathematical approach, one that employed a nascent form of trigonometry based on a function they called Jaya, the precursor to our modern sine. These Indian tables were computationally more elegant, yet the underlying cosmological theory was less developed than Ptolemy's. Both traditions, Greek and Indian, provided powerful tools, but they also contained observational inaccuracies and were calibrated for different longitudes. Ptolemy for Alexandria, the Siddhantas for cities like Ujjain. The task facing al-Khwarizmi and his contemporaries was to forge a new synthesis, a definitive astronomical handbook, or Z, for their own time and place. Al-Khwarizmi's response to this challenge was the Z al-Sindhind, a monumental work whose title, meaning the astronomical tables based on the Indian method, openly declares its primary inspiration. This was a profound act of intellectual consolidation. He took the powerful computational engine of Indian trigonometry and integrated it into the robust theoretical framework of Ptolemaic astronomy. His work was a critical adaptation, a recalibration of the cosmos for the meridian of Baghdad. By adjusting the tables to his local longitude and incorporating fresh observations made at the city's al-Shamsiyya observatory, He produced a tool of immediate and immense utility for the empire's religious officials, navigators, and fellow scientists. The true revolution within the al-Sindh lay in its wholehearted embrace and systematization of trigonometry. Ptolemy's method of chords involved calculating the length of a straight line, connecting 2 points on the circumference of a circle. While geometrically sound, performing a series of calculations with chords was an arduous process, demanding immense patience and leaving ample room for error. The Indian concept of the sine, or jaya, was a far more direct and versatile tool. It defined a relationship between an angle within a right triangle and the ratio of the length of the opposite side to the hypotenuse. Al-Khwarizmi recognized the superior computational efficiency of this approach. He compiled what are believed to be the first extensive tables of the sine function in the Islamic world, a foundational resource that dramatically streamlined astronomical calculations. His tables went further, including values for the cosine function, which is the sine of the complementary angle, and according to some manuscript traditions, the tangent and cotangent as well. With this trigonometric toolkit, problems that were once monumental geometric puzzles became accessible algebraic procedures. Consider the vital task of determining the Qibla, the direction of Mecca. From any given city, this requires solving a complex problem in spherical geometry, relating the city's latitude and longitude to those of Mecca. Using Al-Khwarizmi's sine and cosine tables, this calculation, while still demanding, became a manageable and repeatable process. The abstract beauty of the trigonometric functions found a direct and sacred application, allowing millions of faithful across a vast empire to orient themselves with mathematical precision. The influence of the al-Sindh was immediate and enduring. It became a foundational text, studied and commented upon by generations of Islamic astronomers who followed, including luminaries like al-Battani, who would further refine the trigonometric functions and their applications. When the intellectual currents of the Islamic world began to flow into medieval Europe, Al-Khwarizmi's astronomical work was among the treasures transmitted. Translated into Latin by Adelard of Bath in the 12th century, his tables introduced European scholars to the power of the sine function, displacing the cumbersome Roman numerals and the chord-based geometry that had dominated their own tradition. This transmission laid essential groundwork for the later European development of trigonometry as a distinct mathematical discipline by figures like Regiomontanus, and ultimately for the scientific revolution itself. In his astronomical work as in his algebra and arithmetic, Al-Khwarizmi's genius was that of a master synthesizer and a brilliant pragmatist. He assimilated the most potent ideas from different cultures, refined them and forged them into a coherent system designed to solve the pressing problems of his society. The act of charting the heavens with unprecedented accuracy was intrinsically linked to the parallel challenge of mapping the world below. The same mathematical principles that could locate a star in the sky could, with equal power, pinpoint a city on the surface of the earth, a task that would command the next phase of his scholarly endeavors. This powerful transference of celestial principles to terrestrial matters found its full expression in Al-Khwarizmi's contributions to geography and cartography. The intellectual imperatives of the House of Wisdom were matched by the practical demands of the Abbasid Caliphate, an empire whose vast administrative, commercial, and military reach required a far more precise understanding of the physical world than inherited traditions could offer. The classical maps of the past, while works of genius in their own era, presented a worldview centered on the Mediterranean and contained significant distortions that became increasingly problematic for a civilization whose center of gravity lay in Mesopotamia and whose interests extended deep into Asia and Africa. The foundational text for all serious geographical work of the period was Claudius Ptolemy's 2nd-century masterpiece, the Geographia. It was a monumental achievement of antiquity, the first to use a systematic grid of latitude and longitude to map the known world. Its influence was pervasive, providing the very framework for how educated individuals conceived of global space. Yet for the scholars in al-Ma'mun's Baghdad, the Geographia was a living document to be engaged with, tested, and improved, a starting point for inquiry. Its limitations were becoming apparent. Ptolemy had famously overestimated the longitudinal length of the Mediterranean Sea by a substantial margin, an error that consequently compressed the expanse of Asia and skewed the entire map of the known world eastward. His depiction of the Indian Ocean as an enclosed lake, bounded by a southern land bridge connecting Africa and Asia, flew in the face of contemporary accounts from Arab mariners and merchants who regularly plied its open waters. The Caliphate's administrators, tasked with governing territories from the Iberian Peninsula to the Indus Valley, needed reliable data for taxation, communication, and strategic planning. They required a geography grounded in the empirical realities of their own time. It was to this grand challenge of reconciling ancient authority with contemporary observation that al-Khwarizmi directed his formidable systematic intellect. His response was the Kitāb al-Ar, or the Book of the Image of the Earth. This work stands as a landmark of scientific geography, functioning as a comprehensive gazetteer and a systematic correction of the Ptolemaic model. Al-Khwarizmi took Ptolemy's coordinate system as his structural foundation, but proceeded to repopulate it with new, more accurate information. He produced a meticulously organized list of coordinates for approximately 2,400 localities, including cities, mountains, rivers, islands, and seas. This was a database of the world, rendered in textual form. The sources for these corrections were diverse and reflected the cosmopolitan reach of the Abbasid Empire. Al-Khwarizmi and his colleagues at the House of Wisdom had access to a wealth of new information unavailable to Ptolemy in 2nd century Alexandria. They consulted reports from travelers, merchants, and government officials who had journeyed along the Silk Road, sailed the Indian Ocean, and administered the far-flung provinces of the Caliphate. This infusion of fresh empirical data allowed al-Khwarizmi to produce a world picture that was substantially more accurate. He corrected Ptolemy's exaggerated Mediterranean, refined the coastlines of Africa and Asia, and depicted the Indian Ocean as the open sea it was. The work provided a far clearer image of the Islamic world and its surrounding regions, making it an invaluable tool for the state. The book's structure, a systematic listing of places with their associated coordinates, reveals a profoundly algorithmic mind at work. It represents a way of organizing spatial information that is a clear intellectual ancestor to the databases that underpin our modern geographic information systems, or GIS. The principle of associating a unique data point, a coordinate pair, with a specific geographic feature is precisely the logic that enables digital mapping today. The ambition to accurately map the Earth was inseparable from the ambition to accurately measure it. Perhaps the most dramatic illustration of this empirical spirit during al-Ma'mun's reign was the organized scientific expedition to determine the planet's circumference. The project was an undertaking of remarkable sophistication and logistical complexity, reflecting the immense resources the Caliph could marshal for scientific pursuits. The account of this endeavor, in which al-Khwarizmi was a leading participant, describes a brilliant application of geometry to geodesy. The Caliph's astronomers and surveyors were dispatched to the flat, open plains of Sinjar in modern-day Iraq. There they established a precise starting point. From this central location, one team traveled due north and the other due south. Their task was to proceed in a straight line, carefully measuring their distance traveled until they observed that the altitude of the pole star had changed by exactly 1 degree. This celestial measurement confirmed they had traversed 1 degree of latitude along the Earth's surface. Once this was accomplished, they meticulously recorded the terrestrial distance covered. By multiplying this measured length of a single degree by 360, the total degrees in a circle, they could calculate the entire circumference of the planet. The results were astonishing. The figures they obtained, around 57 Arabic miles for 1 degree of latitude, translate to a calculation for the Earth's circumference that is remarkably close to its modern accepted value, with an error of only a few percent. This achievement stands as a powerful testament to the collaborative, state-sponsored, and deeply empirical nature of science in 9th century Baghdad. It demonstrated a profound confidence in the power of human reason and measurement to grasp the true dimensions of the cosmos. Through the Kitāb and his involvement in the geodetic survey, al-Khwarizmi helped redefine the science of geography. He moved the discipline toward a greater reliance on contemporary observation and systematic data collection, establishing a new standard for cartographic accuracy and utility. The same mind that had brought order to the abstract world of numbers and equations applied its principles to bring a new, more precise order to the physical world. This comprehensive intellectual project, which spanned the creation of abstract algebraic methods, the codification of arithmetic, the charting of the stars, and the mapping of the Earth, constituted a monumental synthesis. The next chapter in this story concerns how this extraordinary body of knowledge, forged in the intellectual crucible of Baghdad, would eventually be transmitted to a nascent Europe, where its concepts would ignite a revolution in thought and lay the very groundwork for the modern scientific age. The intellectual currents of the medieval world, like the great trade routes they so often followed, carried more than spices and silks. They carried ideas, systems of thought, and entire paradigms of understanding. The corpus of knowledge assembled by al-Khwarizmi in 9th century Baghdad, a comprehensive framework for ordering the cosmos, the Earth, and the very nature of quantity, was poised for its own remarkable journey. This voyage would carry it across the Mediterranean to the burgeoning intellectual centers of a Europe stirring from a long slumber, a continent hungry for the wisdom of the Islamic Golden Age. The transmission of this knowledge, and its subsequent assimilation, would forever alter the trajectory of Western thought, planting the seeds from which the scientific revolution would eventually bloom. The primary conduits for this transfer were the vibrant, multicultural cities of Islamic Spain, Al-Andalus, and Sicily. In the 12th century, Toledo, having recently come under Christian rule, became an unparalleled center for translation. Scholars from across Europe, figures like Adelard of Bath, Gerard of Cremona, and Robert of Chester, flocked to the city, drawn by the promise of its vast libraries, filled with Arabic manuscripts preserving and expanding upon the wisdom of the ancient and Eastern worlds. Here, they encountered the works of al-Khwarizmi, and they immediately recognized their transformative power. In 1145, Robert of Chester completed the first Latin translation of the Kitāb al-Mukhtaṣar, fi Ḥisāb, al-Jabr wa-l-Muqābala. He titled his translation Liber al-Jabr et al-Mukhābala, introducing a new word into the European vocabulary. Algebra, derived from the Arabic al-Jabr, the process of restoring or completing, became the name for this powerful new science of equations. For the first time, European thinkers had access to a systematic, generalized method for manipulating unknown quantities, a universal key for unlocking a vast category of quantitative problems previously approachable only through ad hoc or geometric means. A parallel process unfolded with his work on arithmetic. When his treatise on the Hindu-Arabic numeral system was translated into Latin, it was often titled Algoritmi de numero indorum, meaning al-Khwarizmi, on the Indian art of reckoning. The name of the author, algoritmi, became inextricably linked with the process he described. The art of calculating with the new numerals, a step-by-step, procedural method, came to be known as algorithm. Over centuries, through the slow, subtle evolution of language, this term broadened in scope, eventually giving us the modern word algorithm. It is a quiet irony of history that the name of a single Persian mathematician, laboring in the House of Wisdom over a millennium ago, has become the designation for any finite sequence of well-defined, computer-implementable instructions, the very essence of the digital age. The man became the method. The arrival of these texts in Europe was less an addition to existing knowledge and more the introduction of a new operating system for the intellect. The cumbersome Roman numerals and the reliance on the physical abacus for calculation gave way to the fluid efficiency of positional notation and written computation. The geometric and rhetorical approaches to solving specific problems were superseded by a powerful, abstract symbolic language capable of generalization. This new toolkit, comprising algebra and algorithm, was the essential prerequisite for the great intellectual movements to come. It facilitated the complex calculations of Renaissance commerce and finance, enabled the precise engineering of cathedrals and fortifications, and provided the mathematical language for the new astronomy of Copernicus and Kepler. The physics of Galileo and Newton, which described the universe in the language of equations, is unthinkable without the foundational grammar first codified by al-Khwarizmi. To view al-Khwarizmi's achievements as a series of discrete inventions, however, is to miss the deeper structure of his genius. His most profound contribution lies in his role as a master synthesizer. He stood at a unique confluence of civilizations, a nexus where the intellectual traditions of India, Persia, Greece, and the burgeoning Islamic world met. His brilliance was his capacity to recognize the latent power within these disparate streams of thought and to forge them into a coherent, practical, and universal system. From India, he adopted the revolutionary positional numeral system with its elegant place-value concept and the profound utility of zero. From the Greeks he inherited the spirit of axiomatic reasoning, the drive to establish general cases and logical proofs that move from the known to the unknown. From the long tradition of Persian and Babylonian astronomy, he understood the importance of meticulous observation and the systematization of vast quantities of data. Furthermore, his work was deeply embedded in the practical concerns of his own civilization. The Islamic world of the 9th century required sophisticated mathematics for a host of reasons, from determining the Qibla, the direction of prayer toward Mecca, to the intricate calculations of Islamic inheritance law, the ilm al-Fara'id. This legal science, which demanded the precise division of estates according to complex Quranic rules, presented exactly the kind of problems involving unknown shares and fixed relationships that algebra was perfectly suited to solve. His algebraic methods provided a procedural certainty, a clear path through labyrinthine social and economic questions. His genius was in seeing the universal abstract method lurking within the specific practical problem he was solving for the needs of a great empire, and in doing so, he developed a tool for all humanity. Ultimately, the enduring legacy of Muhammad ibn Musa al-Khwarizmi is the very idea of procedural thinking made manifest. He codified the notion that complex problems, whether in commerce, law, or the celestial sphere, could be broken down into a sequence of finite, logical steps. He established a framework where the procedure itself, the algorithm, held the power. This abstraction of method from context is the foundational pillar of modern science, engineering, and computation. It is the intellectual DNA that connects the House of Wisdom in Baghdad to the laboratories of MIT and the data centers of Silicon Valley. Al-Khwarizmi's work is the silent, elegant engine driving much of the modern world, a testament to the power of a single mind to synthesize the wisdom of ages, and in doing so, to define the logic of the future.
We really appreciate you tuning in to this AI-powered presentation. Our goal is to push the boundaries of AI in content creation, and your input is invaluable. If there's a particular subject you'd like to see us tackle next, or if you have suggestions on how we could fine-tune our AI's creative prompts, please don't hesitate to leave your ideas in the comments section. We're excited to bring you more unique content very soon.